Let's jump into the nano world today. It's so small we can't even see it with our eyes, like the circuits in our phones and computers.
Yeah.
And get this, the thing making them smaller and faster is light. But not regular light, extreme ultraviolet, they call it, EUV.
It is pretty amazing. That light is only like 13.5 nanometers. That's really, really tiny. We're using something super tiny to build all the tech of the future.
It's mind-blowing when you think about it. So how does EUV lithography even work? What makes it so different?
Well, it all goes back to Moore's law. Remember, the number of transistors on a chip doubling every 2 years. For a long time, chip makers used deep ultraviolet light, or DUV, to make those transistors, but we ran into a problem when we wanted more power in smaller devices. DUV light, the waves are longer, and it started to cause diffraction.
Diffraction, that's the bending of light, right?
Yeah.
Kind of like when waves hit something.
Exactly. Think about drawing a really thin line with a thick marker. It'll be blurry and spread out. That's what happened with DUV light. It couldn't make those tiny features anymore.
So EUV, with its super short wavelength, comes in to solve the problem.
Yeah, you could say that. Scientists worked for decades trying different light sources, and EUV was the answer. It's like switching from a thick marker to a really fine pen. You get way more precision.
Makes sense. But I'm guessing using this extreme ultraviolet light is not easy. What were some of the challenges?
Oh, tons of challenges. EUV gets absorbed by almost everything. Air, glass, anything really. It's very sensitive.
So how do you work with something like that?
It was a huge challenge for the engineers. They had to basically invent a whole new way to manufacture things. The entire process needs to be in a vacuum, which makes it a lot more complicated and expensive.
It sounds super complicated. And how do they even create EUV light? Doesn't sound like something you can just, find lying around.
No, definitely not. It's a pretty wild process, using lasers and molten tin. You heard right, tin? They shoot these powerful lasers at little drops of molten tin.
Make a tin, like stuff in cans.
Yep, the same tin. They tried like over 100 different materials, but tin was the best at turning laser energy into EUV light.
Wow, zapping molten tin with lasers to make the special light. That's seriously cool. What happens next?
Well, that energy burst turns the tin into plasma, and that plasma makes the EUV light. But then we hit another challenge. How do you focus light that gets absorbed by basically everything, even lenses?
Yeah, that's a good question. I'm guessing they had to come up with a clever solution.
They did. No more regular lenses. EUV lithography uses something much more advanced, multi-layer mirrors.
Multi-layer mirrors, what are those and how do they work?
Picture like a stack of super thin layers, alternating molybdenum and silicon, and each layer is thinner than a strand of DNA. They're arranged to reflect EUV light super efficiently.
So each layer bounces the light to the next, sort of like a chain reaction.
Right. It's like a carefully planned dance of light, keeping the EUV moving without losing much energy. Of course, some light does get absorbed with each bounce.
Right, I can imagine. So how much light do they actually get?
Yeah.
Seems like it'd be tough to get enough EUV to do anything useful.
It is tough. Each reflection absorbs about 30% of the light. But reflecting 70% per mirror is a huge accomplishment, especially since the mirrors have to be so incredibly precise. I'm talking about imperfections smaller than the wavelength of the light.
Wow, 70% is a lot more than I thought with all those challenges. How many mirrors are we talking in a typical setup?
It depends on the specific system, but usually it's at least a dozen mirrors, each one perfectly angled to keep that EUV light on the right path.
That's amazing. So we've got this EUV light, we're bouncing it off super precise mirrors. What's next? How does this actually make those nanoscale circuits on a chip?
That's where the photomask comes in. It's like a stencil with the circuit pattern on it. But here's the catch. Unlike regular photomasks, the ones for EUV have to be reflective.
Reflective, why is that?
Well, remember, EUV gets absorbed by almost everything, so a normal mask wouldn't work. The light would just get absorbed, not pass through. So the EUV photomask has those same multi-layer coatings as the mirrors to reflect the light.
So the EUV light bounces off this mask with the circuit pattern, and then what happens?
That reflected light with the circuit pattern gets projected onto the silicon wafer. But the wafer isn't bare. It's coated with a special light-sensitive stuff called photoresist.
Ah, photoresist. That's the material that reacts to light and lets them create the pattern on the chip, right?
You got it. Where the EUV light hits the photoresist, it causes a chemical change, and that lets them remove specific parts of the photoresist. That's how they etch that circuit pattern onto the wafer so precisely.
It's like the EUV, bouncing off the mask, creates a shadow image of the circuit on the wafer. It's unbelievable how they control light at such a tiny scale. But with all this complexity, it seems like there's a lot that can go wrong.
Oh, for sure. Remember that debris from the tin plasma we talked about? That can mess up those super precise mirrors. Even a tiny flaw can distort the image on the wafer. And then there's the whole vacuum thing, which, as you said, is a huge logistical hurdle. Plus, making those perfect mirrors is an incredible engineering challenge.
It sounds like even with the amazing potential of EUV, there are still some big challenges.
Definitely. But that's always the case with cutting edge technology, right? It's this constant push to improve, find solutions, and overcome limitations. And with EUV lithography, the stakes are incredibly high.
Yeah, we're talking about the future of electronics here.
Exactly. So there's tons of research going on to tackle these problems. Scientists are working on ways to deal with debris, better ways to clean the mirrors, and even better photoresists. It's like a race to perfect this technology and see what it can really do.
It feels like we've only just dipped our toes into this EUV world. There's so much more to learn, from all the cutting-edge research to how this technology will affect our lives.
You're absolutely right, and that's what we'll be getting into next.
I can't wait. This is one of those deep dives that makes you appreciate the amazing ingenuity behind everyday tech.
It really is something, you know? All this amazing engineering, the science, all happening at a scale that's almost impossible to wrap your head around. But it really boils down to that urge to make things smaller, more powerful, and just better, you know?
That's what I find fascinating about tech, this constant push to do more with less. But what's the bigger picture here? What's the point of making things so small?
It's not about shrinking things for the sake of it. It's about, like, unlocking this whole technological revolution. Think about it. Smaller transistors mean you can cram more of them onto a chip. More processing power, faster speeds, less energy use.
So it's not just about making gadgets smaller, it's about making them better in every way.
Exactly. And these improvements, they change everything. Faster phones, more powerful computers, self-driving cars that can think in real time. Even fields like AI, they need massive computing power, and this helps with that.
Wow, so EUV isn't just about sleek gadgets, it's pushing the limits of what's possible with technology. It's like making science fiction into reality.
And the exciting thing is, we're just getting started. Researchers are working on ways to make EUV even better, to push miniaturization even further.
How much smaller can they go? It seems like we're already working at the atomic level.
You'd be surprised. One of the most exciting areas is high NA EUV. NA, that's numerical aperture, and it basically controls how much light the system can gather.
So higher NA, you can focus the light more precisely and make even smaller features on the chips.
That's the goal. High NA EUV systems are still being developed, but they have the potential to, change chip manufacturing all over again.
It's mind-blowing. We're manipulating light at such a tiny scale to build the tech that runs our world. It makes you realize how much we depend on the ingenuity of these scientists and engineers.
It's a testament to what humans can do. We're taking our knowledge of physics, pushing it to the limit, and creating something truly amazing. And that's what makes this field so exciting. Always something new to find out, a new challenge to take on.
It's like an endless frontier, but at the tiniest scale imaginable. Makes you wonder what's next for EUV, what amazing tech it will bring us in the future.
The million-dollar question. It's tough to predict the future, but one thing's for sure. The drive to innovate never stops. There are some brilliant people out there working on the next generation of EUV technologies.
I bet they have some pretty wild ideas in the works.
Oh, absolutely. Imagine devices so small and complex that they, blur the lines between biology and technology.
Now that's a thought-provoking idea, like
Yeah.
tiny machines working inside the human body.
Exactly. It might sound like science fiction, but with EUV pushing the boundaries of what's possible, who knows what the future will bring?
This whole deep dive has been eye-opening. I never knew this world existed, this intricate interplay of light and matter at the nanoscale.
I'm glad you're enjoying it. It's always fascinating to take these complex topics and realize, at their core, they're about using the laws of nature to make something new and incredible.
So with all this potential, are there any downsides to EUV lithography? Any potential challenges or ethical considerations?
That's a great question. Like any technology with this much power, it all comes down to how we use it. EUV could lead to incredible advances in medicine, communication, clean energy, you name it.
It's a reminder that technology itself isn't good or bad, it's how we use it that matters.
Exactly. And that's why it's so important to talk about the potential impact of these new technologies. We need to think critically about the ethical implications, the potential for misuse, and make sure we're using these advances responsibly.
So it's not just about the technology itself, it's about the bigger impact on society.
Absolutely. It's about finding a balance, making progress, but doing it responsibly, using these incredible tools to build a better future for everyone.
This deep dive has given me a new appreciation for the science behind EUV lithography and the ethical side of things, especially with such groundbreaking technologies.
That's great to hear. It's important to remember that technology isn't just about the gadgets. It's how we use them to shape the world around us.
So as we wrap up this exploration of EUV lithography, what's one key takeaway for our listeners to think about?
I think the biggest takeaway is that EUV lithography isn't just a manufacturing process, it's a driver of innovation. It's allowing us to create tech that was once impossible and pushing us to think bigger and bolder about the future.
It's a reminder that even with cutting-edge technology, there's always more to discover, always a new frontier to explore, even if it's at a scale we can barely imagine. It's amazing to think all these tiny circuits made with this light, they're going to power, well, everything in the future. Quantum computers, VR that's like real life, AI that can, actually learn like humans.
It really does feel like we're at the start of something big in tech, and EUV is a huge part of making all that happen.
Okay, but let's get practical for a second. With everything we've talked about, all the complexity and challenges, is EUV ready for the real world? Like, are companies actually making chips with it today?
Yes, definitely. It's not just in labs anymore. Big chip makers like TSMC and Samsung, they're using EUV right now to make the most advanced chips out there.
So the chips in our newest phones and computers, those are probably made with this technology.
You got it. And as it gets better and cheaper, we'll see EUV used even more. It's on track to be the standard way to manufacture the best, most efficient chips for everything.
That's incredible. But we've talked about all the amazing stuff. What about the downsides? Are there any unexpected consequences or ethical issues that we should be thinking about?
That's a really important question. Like with any powerful technology, it depends on us, on how we use it. The advances EUV brings, they could lead to incredible breakthroughs in medicine, communication, clean energy.
It's like technology itself isn't good or bad. It's how we apply it that matters.
Right. And that's why we need to have these discussions,
Yeah.
about the impact of new technologies. We have to think critically about the ethical implications, the potential for misuse, and we need to put safeguards in place to make sure these advancements are used the right way.
So it's not just about the amazing tech. It's also about how we as a society handle it.
Exactly. Finding that balance. Progress, yes, but with responsibility. Using these tools to create a better future for all of us.
Well, this deep dive has given us a lot to think about. The science of EUV light, the ethical questions. It's been quite a journey.
It's been great exploring this with you. It's always inspiring to see people get excited about science and technology.
Me too. And I hope our listeners are feeling inspired as well. We've covered so much, from how they make that EUV light to how it might change the future.
It just shows there's always something new to discover, always a new frontier to explore, even if it's so small we can hardly imagine it.
So to everyone listening, hold on to that curiosity. Keep exploring, keep asking those questions, and never lose that wonder at the incredible world of science and technology.
And until next time, keep diving deep.